Okay, the next section is actually out of order in the textbook, but I like this order better. It's about thermochemical equations. So a thermochemical equation is a chemical equation for the reaction, which we've been doing, plus this fact that we're adding the delta H to the end of it. So basically all that makes it a thermochemical equation is it's a chemical equation with the delta H at either side. So this one is endothermic because it's positive, and this is exothermic because of the fact it's negative. Okay? Now, we can manipulate thermochemical equations, and if we basically change the equation in some way, then we can, it also changes the delta H. Now, the next section that we're going to be doing is something called Hess's Law. In Hess's Law, we need to be able to change the chemical equation in order to get it to add up to what we want it to be. So the two manipulations are, if the reaction is multiplied or divided, then delta H is multiplied or divided. If the reaction is reversed, which means that the reactants become the products and the products become the reactants, then all I have to do is reverse the sign of delta H. So if it was negative, it becomes positive. If it was positive, it became negative. So number 60, okay, tells me that carbon disulfide burns in air, producing carbon dioxide and sulfur dioxide. And here's the reaction for it with the delta H, okay? And so it wants to know what is it for the following equation. It does not matter which one of these it is, okay? It will matter when we get to Hess's Law, but I'm just going to use carbon disulfide. So I want to make this carbon disulfide look like this carbon disulfide, okay? And using this manipulation here, is it multiply or divided? So the coefficient here is 1, the coefficient here is 2. How do I go from 1 to 1, to 1/2? How do I go from 1 to 1/2? Well, I divided by 2, correct? Okay, so that's for number 1. Number 2 is the reaction reversed. Okay, here it is a reactant, here it is a product. So yes, it was reversed. Okay, so basically, I'm going to take the negative 177 divided by 2, and I get a negative 538.5 kilojoules for dividing, and then the fact it's reversed, it becomes a positive 538.5 kilojoules. Okay, so this is simply my answer for this reaction, is my delta H becomes a positive 538.5 kilojoules. Okay, I have another example. With a platinum catalyst, ammonia will burn in oxygen to give nitric oxide. So here's my reaction. 4 ammonias plus 5 oxygens goes to form 4 nitric oxides plus 6 waters. I didn't put the phase labels because you don't really need them. Delta H is a negative 96.2, so this is an exothermic reaction. What is the entropy change for the following reaction? Okay. Again, I can choose any species that I want to choose. Just to show you, I'm going to choose NO this time. Okay. So for NO, so I want to make this NO look like this NO. All right, so for number 1, I'm looking at the coefficients. I went from 4 to 1. How do I make a 4 equal to a 1? Okay, so I'm changing in this direction, so I have to change this one, which means that I divided by 4. Okay, so that means that my delta H is equal to a negative 96.2 divided by 4. And didn't pick up my calculator before. So a negative 96.2 divided by 4 gives me a negative 24.05. That's still in kilojoules. All right, here, this is a product. This is a reactant. So therefore, I also reversed it. And so the delta H becomes a positive 24.05 kilojoules. And so no, you don't need to put the positive in there, but I'm just doing it to show the fact that it does become positive. Okay? And that is the end of determining the or manipulating the thermochemical reactions.